Hello, everyone. Hello, everyone. Happy New Year. Great to see you on this Saturday morning. A cloudy Saturday morning with a winter storm watch in Massachusetts. Hopefully, it will not be as bad as they predict. Please, since this is a larger audience, introduce yourself in the chat, where you're from, what you're excited about this year, 2024. Maybe I should start up by saying what I'm excited about. I'm excited about this talk and the series of talks that we're launching into. I'll tell you more about that in just a second. We'll wait a few more minutes. We had, if I'm correct, close to 180 people registered. So we'll give a few more minutes for people to connect. Florida, Virginia, Toronto. Oh my God, it's going fast now. Fort Worth, Ireland, Scotland, Italy. Ciao, Valentina. I went to college for a while in Genova. Parlo l'italiano. Ho studiato l'italiano. But I'll keep it in English now. Buffalo, Maryland, Oakville, Poland. Poland again, Maryland. Wonderful. Let's see. We have 61 people here. That's about a third of the people who registered. I presume more will join. It's annoying when you make the announcements at the beginning and people join just after the announcement, especially when you have an exciting announcement to make. New York City, Durban, South Africa. Thank you for joining from the Southern Hemisphere. God, it's going too fast. I can't keep up with it. Columbus, Arizona. Yes, Elisabetta, I'm also excited. In the Philippines, amazing. Finland. Great. Well, it's 11:03, and one of the things we want to do is stay on time, and we have a really exciting talk. I want to welcome you all. We have an exciting half year of PhysTEC talks ahead, and I'm counting on all of you to spread the word, and also to, each of you try to get one high school physics teacher who is not yet a member of the PhysTEC network to come and join this network. We've grown in the last few years to over 800 physics high school teachers, heavily focused in the US, but spreading internationally, as you could hear. And it would be great to grow the community even more. We need each other. I mean, one of the things we learned from the early days of the PhysTEC network meetings was that many high school teachers, physics high school teachers, feel very isolated because the only one teaching, many of you are the only one teaching physics in your high school district, don't have really many people to interact with. And this is a great way to informally interact with each other throughout the year to, learn about new ideas. And the core group that sort of sets the program came up with the idea of really launching into a series of talks. Today's the first one that I'd like to call, more socially responsible physics. And what I mean by that is, trying to bring into the curriculum some societal problems that serve as a way of raising the intrinsic motivation for the learning. I mean, I'm preaching to the choir. I don't need to tell you that physics is an important science because it is at the basis of many of the advances of society, from medicine to technology, engineering. But at the same time, it's a science that helps us address major societal problems. And the one that will be the theme for this coming semester is climate change. So in the next starting today and then in the next few months. You may want to jot down the notes. Sarah will put them in the chat. On March 2nd and March 23rd and April 27th, we'll have a series of talks that connect climate change and the high school physics curriculum. So I am truly, truly, truly excited to kick that off today. And I'm going to hand it over to Rob, who played an instrumental role in helping catalyzing this effort, to introduce our speaker today. So welcome again. I hope to see you at all those dates, and I'm truly excited about this development. Rob, I hand it over to you.
Thank you very much, Eric. So again, welcome. It's so good to see so many faces from all over. Today's talk is fabulous. Just a little intro. So Danielle was the 2022 National PhysTEC Teacher of the Year. I had the luxury of meeting her and seeing her talk actually in Vegas, similar to Joe, who was our last speaker. She uses the ISLE approach, which she's going to talk about, investigative science learning environment in the classroom. And I'm going to leave the rest of it to her. I don't like to give any spoilers. So without further ado, here is Danielle.
Thank you very much, Rob. Let me just get this up and we'll be good to go. So, and thank you to everybody for the opportunity to come and speak a little bit with you today. And I'm going to be talking about cultivating growth mindsets of high school physics learners and thinking and failing like a scientist. So as physics educators, what do we want for our students? We want them to love physics, right? Okay, fine. They might not love it, but when they leave our classrooms, we want them to be confident, independent thinkers. If you think about the current state of the world, future jobs are going to require problem solving, collaboration, and creative thinking, not people following procedures, not simply regurgitating facts. Think about what happens in the real world. Think about what we do as educators. How does all of this happen? So what I want to do today is I want to take you into my classroom and share some of the processes and procedures that are embedded in the learning that help my students cultivate growth mindsets that they can use later in their lives. And come on, there we go. So to do this, I'm going to break this talk into 3 parts. First, I'm going to provide some background context on the theoretical framework that I use. Then I'm going to take you into my classroom and show you how I use it. And finally, I'm going to talk about some next steps. What do students transfer to their lives outside of the classroom? And what new global contexts can they apply this mindset to within our classroom? And in that last part, I will talk a little bit about the climate change game that Alana Resnick and I created. Okay, so step 1, yeah, there we go, background. So the theoretical framework that I'm following in my classroom is the investigative science learning environment, or ISLE, as Rob mentioned. And I know there's a range of familiarity with ISLE, so I'm going to provide a brief overview, and then I will share a slide at the end of my talk with some more resources for people who'd like to learn more. So ISLE is one way that we help our students learn to think like scientists. It's an intentional approach to curriculum design and learning, and it has 2 core intentionalities. One, that students learn physics by practicing it, and the other is that their well-being is enhanced in the process. So if we want our students to learn physics by practicing it, they need to engage with the same methodologies that professional scientists use on a daily basis. Think about the world around us. A lot of science starts with an observation. We then look for patterns in the data, and we come up with possible explanations or hypotheses. But we can't accept these explanations as true at face value. No, we can't just say, well, I like that one, I'm going to use it. The students have to design experiments to test these different explanations. And before performing the experiment, though, they have to make a prediction based on the possible explanation of what the outcome is going to be, not their intuition. It's an idea based on patterns in the data that's being tested, not someone's thoughts, which is going to help them with their well-being. If these outcomes don't agree, then this is the fun part. The students can say that they disproved an idea, and they have to go back, and they have to make more observations, they have to revise their assumptions, and they have to propose different explanations. If they agree, okay, we perform more testing experiments, and if all of those agree as well, finally use this explanation for applications. Okay, I want to go through a quick physics example. In the waves unit, we begin with an observational experiment. The student groups are asked to create 2 equal amplitude pulses at opposite ends of the slinky and describe what happens when they meet. The students typically invent two possible explanations for this motion, that the pulses either pass through one another or they bounce off one another. And again, now that we have these multiple explanations, we can't just say, I think it's this one and move on. They have to test them out. But in order to test them, like I said, they have to design these testing experiments. And they typically will arrive at the conclusion that they either have to send unequal pulses on the same side of the slinky or send pulses on opposite sides of the slinky towards one another to test these ideas. So this particular student group chose to send two pulses on opposite sides of the slinky. And before performing the experiment, they're reminded they need to make a prediction about the outcome based on the two explanations. So as you can see here, they drew out what would happen if each explanation were true. If they bounce off one another, the pulses will return to their origin. They pass through one another, they'll continue moving across the slinky. So now we perform the experiment and we make a judgment about the outcome. As shown here, the hypothesis that the wave pulses pass through one another is supported, and the bounce off hypothesis is disproven. The students can now design more experiments to test this idea further, and eventually they can use it in real world applications. And this is that process that we want our students to go through when they're learning physics. But as a teacher, in addition to this process, we have to ask our students, what is the purpose of the work we're having them do? Why are they doing this? So if our goals are for them to learn to think like scientists, to feel good about themselves in the process, to grow as a learner, and to be able to transfer this to other aspects of their lives, in addition to working with them on these processes, we also have to help them develop positive affect about learning. One way to do this is establishing a classroom culture where it's okay to be wrong, where you're testing patterns in data, not someone's ideas, where you want a surprising result and you want them to figure out what is actually happening. And to do this, the classroom needs to provide them a lot of opportunities to revise their thinking. It can't just be one and done. It has to be naturally integrated into the learning process. It can't seem like it's forced or is just put there as an afterthought. It's a lot easier to show you what I'm talking about than to go through this theoretically. So let's go into my classroom. Welcome. These are some of my students. My classroom is loud. It's sometimes chaotic. Okay, it's often chaotic, but it's really collaborative and really productive. I teach an incredibly diverse population of students. Some of my physics classes contain students who lack confidence in science and themselves, and the others contain high-achieving students who always have to be right. They're never wrong. So I have to shift mindsets on both ends of the spectrum. And to do this, first and foremost, the classroom culture has everybody viewed as an equal. Everybody has something to contribute to their learning. All these contributions are valued. So for me, it comes down to teamwork. Think about us right now. We're a community of physics educators. Think about scientists. They're in a community. We want our students to be part of a community of physicists. Everything in the classroom is done in teams. They're constantly working together to construct this knowledge. They have that support. They have those interactions. So as a teacher, I have to make sure that they have tasks that require both conceptual and procedural understanding, and too much for one person to do on their own. They have to learn how to work together. These are our teenagers. They're our high school students. Sometimes that means assigning roles. Sometimes that means they assign the roles to each other and taking accountability for their actions in the group, being responsible. In this setting, my role as the teacher is that of a facilitator. I have to work to facilitate this positive interdependence so that for my students, working together becomes a natural part of the learning process. And to do this, I have a lot of support structures in place. While they're working together, I love it. And in my classroom, we have a lot of whiteboards. And most of them are usually filled with physics, which is great. The students really come to recognize that there's something that makes whiteboarding feel less permanent. If you write on the board, you feel your ideas are editable. You can go back, they can revise their thinking. It's not, oh, this is what I did and I'm turning it in. They can look at something, grab an eraser or their hand and change it right away. And also, I can see their thinking. I can walk through the classroom. I can see what they're doing, lean over, and if I need to, I can ask these fallback questions so that they can activate that prior knowledge to help move themselves forward. There's also a lot of physical activity in the room. Remember, I said it's a little chaotic. They're up and they're moving, and there's a lot of chances for them to demonstrate their understanding without writing anything down. We will act out diagrams all the time. I might ask them to show me what a position time graph looks like with their hands. At first, as you can imagine, they're going to be very shy. You're going to see kind of low hands below the table, or maybe a couple fingers. They're kind of looking around at each other because remember, they don't want to be wrong. But after a while, you see them looking at each other, not to see who's putting something up, but to see how their response compares to a different student's. And they'll turn to each other and voluntarily support their peers. They'll say how to modify it. If you look at the image I have on the left here, if you notice, 2 of my students are facing forward and 2 are facing back. The 2 facing towards the wall initially had their diagrams the opposite direction. And the students behind them said, hey, no, we established our coordinate system is this way. We established that the person was exerting a force this way. You might want to switch. So instead of moving their hands, they just turned around, which is fine. But they're looking for consistency amongst each other. They're not looking to me for it to be constant. They're looking at each other for this. We're also going to play some games. The students in the middle are playing a heads up game where they each have a graph on their taped to their headband. Some are position time, some are velocity time, some are acceleration versus time. And they have to go around and figure out not only which graph they are using without someone directly telling them, but they also have to figure out which other graphs are consistent with the motion described for them. And in this case, they can't just rely on 1 or 2 of their friends. They have to go talk to everybody because everybody has something, information or support they might need in the classroom. And finally, physically engaging with these experiments. The picture on the right has one of my students pushing our student teacher from last semester with using a bathroom scale, because we asked for developing Newton's second law for her to exert a constant force. And for our students, when they hear constant, they think it's the same. They think nothing's going to change. So of course, without the scale, she's pushing and she's moving at a steady pace and the student teacher is moving away from her. So we gave her the bathroom scale. And what's great about this is when she realized she had to push with the exact same value on the scale the whole time, instantly she was getting that change in her mind of what constant meant and how it could be different for forces than it was for velocity. And this gives them a chance to change their thinking in that moment. Now, after doing all of these experiments, after doing all of this group work, they're going to share things out. And we'll have symposiums. Either one group will present to the class, or we'll do like a gallery walk or a poster session where they walk around the room and they can ask questions of each other. And this is a safe space for my students because they can have smaller conversations. So those quieter students may feel more supported with their peers. It's not in front of the whole class. But in this setting, they're learning how to give and receive feedback. It's not criticism. It's not a critique of you're doing this wrong and I'm doing this right. It's, hey, something looks a little bit off here, or this is really great. How did you do it? And then they're coming back to their groups with what to change. And they're making modifications based on their peers. So there was a lot going on here in the classroom. And I want to have additional support structures in place aside from just talking to each other. So one of these support structures are rubrics. And this is a great resource for them for self-assessment. And these rubrics are known as scientific abilities rubrics, where the scientific abilities are these processes and procedures that scientists engage with on a daily basis. And there are 7 overarching scientific abilities. And each of those abilities has sub-abilities that have rubrics with them. And the students can use these sub-abilities in order to evaluate the work that they're doing in the classroom. So this is an example of one rubric, and it pairs with this lab. And at the beginning of the dynamics unit, we will do an investigation where the students will have to explore how water interacts with an object submerged in it. And they're given a bottle filled with sand, a bucket of water, a spring scale, a ruler, and they're going to pose some questions about how the water interacts with the bottle. And they'll put all their work up on whiteboards at first, then they'll type it up later. And with their work, I'm asking them to show me where they're meeting the different rubric criteria. So if you see there's some numbers circled on here, those are the different rubrics that they're working with. And they're saying, this is the evidence for me doing this on my investigation. And I'm just going to blow one of those up for you to kind of see. The rubric I showed before, like I said, was the ability to decide what's to be measured and identify the independent and dependent variables. So in this group, I just zoomed in on it, but I also typed it up for you because I know it's a little hard with student handwriting. So their independent variable is how the depth at which the bottle's submerged. And their dependent variable is the force exerted by the spring scale on the bottle. And not only do they tell me what their variables are, but they're saying they're saying the reasoning for this is that they can control the depth at which the bottle's submerged. So that's going to be their independent variable. And for this, they would earn a refining on this. So the students are self-assessing. They're revisiting what they're doing constantly in their groups, but they're doing a lot in a class period. They're doing a lot in a week. So we want them to reflect. We want them to have that metacognitive time to say, what did I actually learn today? Or what did I learn this week? And not just what, but how. What did I physically have to do as a learner in order to understand and learn this topic? And then what remains unclear? Because they're going to go home that evening and look at something, or they're going to come back to class the next day, and they're going to want to make sure that they are really knowing what questions to ask or what they have to focus on so that they can move their learning and their understanding forward. So this is one way that I do reflections. A second way is a new project I'm working on with Debbie Andres on student identity and self-efficacy. And we're doing these in the moment reflections where it's a short Google form that they fill out at the end of each class. And it asks them, how do they feel? And there's 5 different options for them to pick from. And based on each option, the students get a different subset of questions to answer afterwards. And these new questions, it'll ask them a little bit more of why they feel that way, and also offer some prompts or suggestions for actions they can take. So if they're confused, it's asking them a series of check off what you did. Did I ask my classmates? Did I go back and look at my notes? Did I ask my teacher? And then what could they do the next day in order to help them if they didn't pick something the first day? So I'm hoping we'll have some insights on this for you all very soon. But they're reflecting daily, they're reflecting weekly, they're reflecting every quarter as well. I ask them to revisit their goals and what did they do in those last 2 to 3 months? And what changes do they have to make in the next 2 and 3 months based on what's happened in the classroom and based on their performance? At the end of the year, we're doing this as well. I'm asking them to see where they are and what they took away from the class. So I pulled a few reflections here that are relating to their mindsets. I shouldn't look at science as my weakness, which is great. Remember, I have students who are not confident in science. I'm more confident in what I'm learning and more comfortable. I'm able to refine my knowledge and establish a good habit. I wasn't incapable. I just had to put in more effort. These are really good reflections that we're having from our students. They're saying a lot of really good things. But this is challenging. Think about what's going on. We're asking our students to think like a scientist, and it's really hard. I'm asking them to change their mindset. They're getting frustrated. They tell me they're frustrated, especially at the beginning of the year. They struggle with understanding how these representations fit together, how to clearly articulate their thinking, and how to evaluate their own work. And recall, this is what happens to scientists. This is what we do as teachers. We're not just told, oh, well, that's what you submitted. We're told to fix it. We're told to do it again. So why shouldn't our students have these same opportunities? And that's what I do in the classroom. This is probably our largest formative assessment component. And like I said before, I'm in a high achieving district. Earning a B, especially in an honors course, is considered failing. So if I'm going to ask my students to challenge themselves, to step outside of their comfort zone, to take risks in their thinking, I have to make it clear that I'm here to support them on their journey, not just in the classroom with those short, quick checks. Failing can't be seen as a be-all, end-all for them. It has to be part of the process. So I allow my students to resubmit their work for up to full credit. And I do this on 2 classroom activities, these checks for understanding and these laboratory reports. And these checks for understanding, they're short, they're formative, 10, 15 minutes, 1 or 2 questions, and I give them approximately once a week. I don't evaluate them with numbers. I use these categories at the top, and I'll say, based on the feedback, this is where you're at right now in your demonstrated understanding. And then they get them back, and they have a chance to recover them. They have a chance to revise. I want them to reflect on, but it's not just, this revision is not just them saying, oh, here's the correct answer. They have to reflect. What didn't they understand while they were doing it? They have to revise the problem. They can talk to each other. They can talk to me. Then they have to reflect again on now, what do they understand? What might be different in their understanding? What were the gaps? And then they have to do some additional practice. I give them questions that are the same concepts or the same processes or the same content, but in a different way. So they're applying it to a new scenario. And they have to do this quickly, Because if I don't give them a deadline, they're going to see what their grade is at the end of the marking period and try to give me all of these. And that's not the goal of this recovery. That's not the goal of these checks. So they'll take them, they'll get them back the next day, and then they have 1 or 2 days to revise. They turn them in, I'll give them some feedback, and then I will usually give them one more chance for this, and the deadline's the next day. After that, we're going to move on. Because for my sanity, as a teacher, I can't keep looking at these over and over, but also they're going to see that content again and again in the course. It's not just a one and done. They're going to see it multiple times, so they will have more opportunities to recover. Additionally, we do this with laboratory reports. After the students complete them in the classroom, they write up on average 2 to 3 formal group reports per quarter. And I use Google Docs for this, so it's a really easy way for them to collaborate. And they're scored using the scientific abilities rubrics. The students self-assess themselves, and then I go back and give them some feedback. I give feedback as comments, also as rubric scores. And as you can see here, the students do their revisions in a different color. This helps me out because I'm not rereading an entire lab report. I'm now seeing what did they change, and I can go back and easily give them more feedback. And I usually give them about a week for this because it takes a little more time to go back. Some of them may need to collect more data because they didn't do that at first. And I'm not expecting you to read any of this, but you can see where they did it and what changes they made. And the majority of the groups choose to revise this. And for my son, like, again, each group gets one opportunity to revise. They have multiple opportunities throughout the school year. And if you do want to learn more about the revisions and what they gain on this, I did just have a paper out in PhysRev at the end of December that talks in detail about students revising laboratory reports. So this really does benefit their mindsets and their ability to think like a scientist. One student reflected this about revisions at the end of the year. Instead of never looking back, it allows me to reflect on my failure and improve my own understanding. They're so busy, they don't take the time to revisit their work and improve their understanding. They just think they can forget about it and move on. But we know that we're working as educators to change their mindsets. So reflections at the end of the year are showing me that students have positive attitudes. They're changing. They're saying that they're growing as learners. But if you remember, we want them, if you remember at the beginning, we talked about what are the goals for education. And we want our students to be prepared for jobs and careers in this new 21st century. So if we want them to take these away, I can see that they're doing this in my classroom, but how do I know they're actually transferring this to new scenarios? So we asked them. I sent a survey out to a lot of IEL students who had taken IEL-based physics classes in high school, ranging from 9th grade conceptual classes up through the AP level. And we asked them what they remembered from the course, what they were using in the course today, and what they were actually doing in their current studies or their careers. And we got back over 200 responses for this, which is really incredible from alumni going 8 to 10 years back. We broke down a lot of their responses into 2 types of transfer: direct application. A lot of students talked about study habits, preparation for college, and critical thinking related to STEM. And then also preparation for future learning, metacognitive skills, learning from failure in their classes and in their careers, critical thinking and how they were using this. And then as well, communication and collaboration, what they developed in this class and how it was helping them in the future. It was really, really good that they're using this beyond the classroom. So a couple of quotes from some students. I became a better advocate for my learning as a result of being challenged and sometimes confused. I'm not afraid to speak up. And a more STEM-based one, learning how to design experiments probably helped me understand scientific papers a lot more and research papers a lot more than just doing an experiment, but with a given protocol or whatnot. So learning how to actually go through this process is helping this student, future past student, with reading and understanding research papers and experiments. And in addition to transferring to their lives outside the classroom, we want them to be able to transfer to new scenarios that are really important for them to understand and be sustainable members of our community. So this requires them to apply both physics knowledge and reasoning. And we want them to think about this idea of resilience when they're exploring something new. Thinking about what about learning to think like a scientist and being comfortable with being uncertain and even wrong can help our students explore new situations and new topics that are really important for them to know, such as climate change. So Alana Resnick and I set out to just start to answer this question. And we created an escape room that's based in Isle for introductory physics students exploring the Arctic. And if you don't know, escape rooms are a series of puzzles where you can be locked in a room, and then you have to, through figuring out these puzzles, through clues that you have to figure out how to escape and get out of the door. And we have a digital escape room. We don't have a physical escape room, but we're focusing on the Arctic. The Arctic, if you didn't know, is currently warming 4 times faster than the rest of the planet. And it really plays an important role in regulating what's going on everywhere. So the phenomenon that we're investigating in this game is thermokarst. And it's the process by which lakes and sinkholes are created due to thawing permafrost, this permanently frozen soil. And it's a really powerful circumstance for our students to investigate, because as this thaws, it releases centuries-old carbon dioxide and methane. And there's really a lot of climate science and physics involved in this. And we want to make it accessible for our students while having them use all of the skills they developed in their physics class. So the main climate idea that students will learn in this game is about feedback loops and how this change in energy exchange causes an increase in the ground temperature, which allows the permafrost to thaw and the lakes to form. They need to be aware of, and we'll learn about, albedo, the reflectivity of the surface. And they're going to explore how this has a direct effect on the amount of outgoing radiation and how that reflected from the surface. They're going to have to explain how this outgoing radiation interacts with the greenhouse gases in the atmosphere, and it becomes trapped. Both of these are going to contribute to the ground temperature, which as it warms will result in a loss of land, as well as the release of these long-stored greenhouse gases, microbes, and potent chemicals. And there's a lot of physics involved in this, but we really chose to focus on 3 topics for the game. First concept that the students need to understand is the law of reflection and the law of refraction. And they're going to need this in order to be able to explain how the incoming solar radiation interacts with the different surfaces. And it's going to help them explain what's absorbed and what's reflected back. Additionally, they're going to need energy for the analysis. And if you're playing this game later in your school year, they should already be familiar with this concept, both at the macroscopic and microscopic levels. Understanding energy transformations is going to help our students explain how this solar energy is being converted to other forms and allowing these stored greenhouse gas particles to be released. And finally, the last concept here is wave behavior. This is including knowledge of the electromagnetic spectrum. And as I mentioned earlier, the greenhouse gases trapped in the atmosphere limit some of this outgoing radiation, which disrupts that feedback loop and creates this positive warming effect. And the students have to understand which wavelengths are being absorbed by the gases, infrared, and all of this climate science, all of this physics that I just gave you as a very brief overview, it's all embedded in the game puzzles. And our game has 3 puzzles. I'm just going to share one of them, but I'm happy to talk more about the other puzzles in the Q&A after. And this is the first puzzle of the game. The students are given authentic data from NOAA in order to explore which of these probes at the research base is sounding the alarm. They're getting data that has new units, new representations for a new context. And yes, the students can just go through and they can guess and they can do trial and error, but they spent an entire year learning how to engage with data and look for patterns and come up with explanations. They also learned how to work together to come up with conclusions. So as educators, we want these skills and we want these mindsets to be transferable to new and unfamiliar scenarios. They're not going to be able to understand the process of the game and really get at the root of it without activating all of those resources they developed during the school year. And we piloted this game before pushing it out and publishing the paper for everybody with Alana's physics students, as well as teachers, and as well as experts in the field. And based on that feedback, we have the version that I'm sharing with all of you today. So very briefly, I promised at the beginning that I want to share a few ISLE resources with you that are available. ISLEphysics.net is your go-to source for all of these. They're all mentioned on there, but there's also the College Physics Explore and Apply textbook, the Scientific Abilities website that has the rubrics, that has some lab materials in there. There's the active learning guide as well that goes with the textbook. PUM is the Physics Union Mathematics middle and high school curricular resources. Additionally, a couple years ago, Eugenia Ekina gave a talk in June of 2021. It's on the YouTube channel if you want to check that out. There's the Explore and Apply Facebook group that has over 2,000 members, and it's very active. If you do choose to join that, there'll be a question asking how you heard about it. Please just say this talk. That way we have educators in there and not students. And then there's also a couple of in-person workshops upcoming if you're in any of these areas. There's one at Rutgers in June, and then the AAPT in Boston is going to also have one July 6th or 7th on one of those workshop days. And talking about AAPT, if you are attending and you are thinking of giving a talk or doing a presentation, AAPT is hosting a coffee hour on February 12th. I think it's at 7 or 7:30 in the evening, working with educators who are interested in submitting a talk on how to work through their abstracts. So if you are interested in that, please check out the AAPT website to sign up for that as well. Thank you very much for your time today.
Thank you very much. Wow. That's what I can say is wow. There's a lot to unpack. So I have two questions that were in the chat that I'll ask first. And if you have questions, you can raise your hand and you'll come up in a list on the right-hand side. And I'll call on you to ask. So we'll start with an easy question that I think was written by Andrew. The question was, how many students do you typically have in a classroom?
Typically, the classrooms have about 20 to 25 students.
Gotcha. And I think you mentioned it, but high school level, right?
Yes, high school. So most of my students at the moment are sophomores through seniors, so that 15 to 18-year-old range of students. And then in our school, we can have up to 5 sections of the course. So I could have 100 to 125 students a year.
Gotcha. So the follow-up question to that, and you brought this up quite a bit about the teacher sanity, which I think is just so important. The question I believe was by Andrea was, do you give the students time to do the revisions in class? And I think just expanding on kind of how that process works and the time associated with it.
So honestly, it depends on the level of the course. It depends on the task that I'm asking the students to work through. In my conceptual courses or the college prep level courses, usually I will give them time in class to go through their labs, to talk with each other, to work on that. So that way they have an idea of what they're doing when they leave the room. For my students at the honors level, I will usually give them maybe 5 minutes or so just to touch base, but they're a lot better about connecting with each other or coming in to see me if they need some help. The checks for understanding, once they take them, they get them back. I don't go over them immediately in the classroom because I want them to look at the feedback. I want them to talk to each other and see if they can figure out what they did prior to me actually going through and saying, oh, this is the answer. Because as we know with our students, a lot of them will look at the teacher solution, say, oh, I got it. And then they'll move on. But they won't really get that chance to reflect if they have to do it, if they're doing it with me. So those I send them home with. I'm always there to support them. I'm happy to answer questions. If they need to come in before school, if they have to come in at lunch, I am willing to work with them on that. But that is something that's done outside of class. And then for making these, I make sure they're questions that I can see my goals and see what I want them to get out of it very quickly. It's not something I'm going to have to sit there and read through everything they did. I should be able to very briefly look at it, less than a minute per paper to be done, just to get that feedback back. And then they get the chance to do the revisions on it. And in going back to one last thing with that, I've done these in many different ways. I've done them where the students have to come in and they have to present their reflections to me. I've done this where they have to come in and solve problems live for me. And over the years with workloads and everything, I have found that some students take advantage of that opportunity. Putting that in, though, does also create a barrier for students who can't come in. And I want to make sure they're having a chance to revise and to improve their understanding and demonstrate that. So I have changed it a little bit over the years where a lot of it will be done independently. But if I feel classes are not doing this, then I will go back to that way of you have to come and talk to me. So I know it's you doing this and you understanding this and not one of your peers just saying, oh, write this down and be done with it.
Love that level of accountability. And actually there's a question by Peter that I think goes to that access question. You're using whiteboards and all of this in your classroom, and I know we all want to do it. And I think he nailed the question. Just what's your average budget on dry erase markers and stuff like that?
I am very fortunate that our school will provide us with dry erase markers for that. So I am very fortunate in that case. If I was in a building where that was not the case, I would probably be doing things a little bit differently. We used to have chalkboards and then everything's transitioned over to that. So I know chalk is a little bit more affordable than dry erase markers. I would also, in that class, I'd be putting that in as a priority in my budget if I didn't have access to that for the school, through the school, as well as if students are there as, I don't ask them to bring supplies in aside from whatever their notebook is. But if I ask each student at the beginning of the year, bring in markers, those are your personal markers. So it's like buying a pen, buying a pencil. They should be able to do that. And obviously, if students can't, having that support system in place so they can work with it. Whiteboards, Home Depot, shower board at Home Depot. If you haven't done this, if you don't know this hack, go to Home Depot, get some of that shower board, tell them you're a teacher, they'll cut them down for you. And they are a really good way to have a lot cheaper whiteboard than buying them from the supply companies.
Yeah. I think those sheets, by the way, it's like $20 for a 4x8 foot sheet. So super, super affordable.
Yeah.
There's a grouping of questions now from a couple people that I think are sort of related. And having known you and the work that you do, there were a couple questions about the physics education research aspect that you implement into the classroom, the high level of teaching. It seems like you're teaching a lot of materials, and how you kind of fit it all in. So I know that teachers are often, I want to do this, but there's so much curriculum to cover. If you can kind of combine all those and tell us how you're able to expand time past the 24 hours in a day.
That's my secret. I can't reveal that. But no, it's about, for me at least, it's about prioritizing what I'm interested in with my students, as well as what I know is going to benefit them. All of the projects that I'm taking on, whether it's the resubmissions, whether it's the reflection, whether it's the self-efficacy, all of these projects, climate change, it's all something that I know is going to better them and benefit them for their futures. And for me as a teacher, I want to do this action research because I want to know if what I'm doing is actually effective. I don't want something being done for my students that's not going to benefit them and that's not going to help them in their future lives. So over the years, I've kind of added different projects in, and a lot of it, the research aspect, a lot of it doesn't happen immediately during the school year. It's something that happens for me during my breaks or during the summers. That's when I do a lot of my research. It's mainly during the year I'm collecting data on it. So when they're doing work, they're doing their laboratories, they're doing their investigations, I'm collecting those, I'm writing down what their abilities are, I'm saving that. And then as I have all of them later on in the year, I'm doing more of that analysis for myself from a research perspective. In terms of the reflections, I do go back and I do go look at their daily reflections to see where they're at, because that's important. And I'm seeing general trends based on my students, but I don't have those concrete answers until later on, because otherwise it's very difficult, as we know, as educators, to balance that plus the full-time job that goes with the research part. So I'd say for me, the research is a little bit slower than the implementation. And I'll modify different projects that we're doing in class. I'll focus on different priorities on different years. If you haven't figured it out based on hearing me talk, I get very excited when we're doing cool things in the classroom. And that's usually how I get myself into these projects, because I'm like, oh, this is exciting. This is really good. What are we actually going to take away from it for the students? So I'm not sure if that actually answered the question, or if you have a follow-up, Rob, that might help direct that further.
I mean, I think it answered my question. It was a combination of 3 people in the chat. So to those people, if you want more, please ask. A follow-up question to that, though, because I do think it's interesting, and I believe Josh had asked this. Within the class and your students and making the groups, do you tend to make the groups? Do you allow them to self-select? What is kind of the atmosphere that you set up in terms of that?
So I do purposely make their groups, but I tell them in September that they're going to work with every single person in the classroom. So at the beginning of the year, for the first couple of days, they get to choose their own groups, and I get to see who they are, who their friends are. And then a couple of days later, I'll split them. I'll take 2 people from each group, so you're at least with one person that you know, and I'll put them together. And then I will, every 6 weeks or so, I'll change them again. And for my female students in the class, I always make sure there's more than one of them in a group. They tend to be my quieter students, especially in the honors level classes. I have a big gender imbalance in the classroom. And I want to make sure those student voices don't get lost, because they have really good ideas. Because I'll walk around and I'll be hearing something and we'll be talking, and one of them will be in the group and they'll say, and we'll get to the conclusion. They'll be like, see, I told you, but the other students aren't listening to it. With the groups, I am purposeful, because after that first few weeks, I learn who my students are. And if I know I have students that will not work well with other students, I won't put them in a group at that point, because I don't want it to be a hostile or a non-beneficial environment for the students. So they're in groups of 3 or 4, because on average, we get 24 in the class. So it gives me 6 groups of 4. If I have a couple less, there'll be a couple groups of 3. And they're used to it. By the end of the year, they're friends with everybody, and or at least acquaintances, and it's very nice.
I love that. And I think that's so important, the fact that sometimes I think we forget that we are the teachers in the classroom, and they're going to follow us because the students don't know any other way. So if you tell them that's what's going to happen, and that's what's going to happen, then that's the thing that happens. In particular, I just want to point out, I really liked how you group your female students. Step Up is another organization that's into that. I know you're familiar with them, and that's just such an important thing towards that student advocacy and that student comfort. It's just nice to hear that pointed out. So a little shift to the other side. The question was asked, for your college prep classes, how deep into the content do you go? And what's your rough breakdown?
In terms of, I guess, topics covered in those classes?
Yeah, that's what the question says. So the question was posed by Kristen, like mechanics and E&M, wave, optics.
Yep. So the conceptual course, our schools had multiple levels of a conceptual course. We had a 9th grade physics first that was for students a lot of those students were in Algebra 1 or Algebra 1 Part 1, or not even in that portion yet. So that level course, we did a lot more conceptual understanding. We didn't do as much of the deep mathematical analysis, but they were doing the same level of conceptual depth as the honor students, because it's physics and they can see it. We're not getting into the angles, we're not getting into the inclines, but they can do that. And for those groups, we'll go through, we'll still do kinematics, dynamics, very conceptual based circular motion. What am I in there? We didn't do gravitation with that group, but I will do that with the junior, senior college prep courses, because they have a little bit more of that math background to be able to do that reasoning. Momentum and energy are in there. And then we get into electrostatics, magnetism. We'll do a little bit of magnetism. We won't go as deep into induction with that group, but they still will do magnetism. The junior, senior course will still do the right-hand rules. And then because those courses don't have those 2D components in there, we can move a little further. In addition to doing waves, we can get into a little bit of optics as well with them. So they kind of get more topics covered in those classes than the honors, where we have more depth in those topics.
And to piggyback off that, this was a question from Kareem. The standards that you use in the classroom, are they state-based or school-based or created by you?
So our school follows the Next Generation Science Standards. So we are using NGSS, and then New Jersey adopted them, but they're the same standards.
Gotcha. Okay, a couple other follow-ups to beginning questions. With the groups, do you mix student abilities? I suppose it means purposefully, or in that vein.
Absolutely. I want there to be a diverse group of students and abilities in each of the groups. I don't want it to be one group of students who just knows everything and one group of students who's completely struggling. I want them to work together with everybody in the room, and for those stronger students to help those students who may be struggling. That being said, if I do notice that I have some of my weaker students kind of just sitting back and not doing anything, and I've noticed this going on, I have in the past taken those students and put them all in a group for one time, and they start to work and they start to figure it out. And then I see them go off and have more confidence when they jump into the other groups, because they actually have to do something at this point. They actually have to do something. And I'll do the same thing with some of my stronger students. Sometimes if we have a topic where I know there's going to be a range in it, a range of abilities, maybe I'll put some of them together so they can go into a little more depth with it beyond the scope of what we're doing in the class.
Love that. Love that accountability. And with that, this was another question just posed. When you're training your students or teaching your students or facilitating in the classroom early on in the year, do you teach the multiple representations first and then the students apply, or are they applying it as they go? What's kind of the process to onboard the students, if you will?
So everything that we're doing in the classroom through ISLE is being introduced to the students as they need it. They're coming up with so they're building the idea of representations as they are going through the content, as they are coming, as they reach that point of needing it. That's where it comes up, and that's where we talk about it. So I'm not going to introduce a force diagram to them before they have an idea of what force is. I'm not going to introduce a motion diagram until they know, just can describe how objects move qualitatively, and then we draw out, oh, this is how we're marking our object. What if we had a simplified way, a unified way that everybody could mark something together and talk about it? And then we refer back to them. I make sure that they have to integrate those into whatever problems we're doing, into whatever activities we're doing, so they can see it not just as something that they're doing because their teacher told them they have to learn it, but it's actually useful. So we're in energy right now, and we're doing energy bar charts, and a lot of them just jump straight to the math, but they're missing parts. I'm like, draw the bar chart. If you draw the bar chart, the math comes straight down. You pull down which energies you have, and you can solve this at any point in time. You can use that representation, and it's useful for you.
I love that. And I think that really highlights the this interplay of that cognitive science that goes with it. Like, it's not all happening at once like many people think it does. As you said, it comes as you need it and you use it. So I think that's an important fact. And I think I've got one more question for you, and this might be the most important question. This was posed by Jolene, and I always love this question. What are your top time-saving tips for new teachers and novice teachers, especially since a lot of us are isolated? This is their moment to get everything that they need to be someone like you.
Top time-saving tips. Making sure that when I'm doing these, when you're doing a check or you're doing like an exit ticket, it's something that you can go through very quickly. It's something that you don't, like I was saying earlier, you don't need to read a lot, read a lot of student work. And because they have the opportunity to revise, I don't have to put that level of deep level of feedback on there. I'm not telling them exactly what they need to change or why they need to change it. So I'm putting a few marks. If they have questions, they can ask, but that gets that back to them very quickly. Another time-saving tip that I found is, as I'm going through activities and lessons in one year, if I find something, is it working right? Revising it and changing it right then. Because I don't want to come back a year later when I hit that same topic and be like, wait, what did I have to change? Because I'm probably going to be busy with something else. Also, I'd say make the schedule for when things are due with the students, when it works for you, so you know you can get it back to them. So with reflections, I would always have my students have them due by Friday evening, because I knew for me, Saturday morning, I'd wake up and I'd read them and I'd be able to give them some feedback if that was something we're doing. As well, work with your colleagues. For new teachers especially, you don't have to reinvent everything that you're doing. There's a lot of people out there with a lot of amazing ideas. There's a lot of resources. Tap into those and use them. And then as you're going through and as you're becoming more confident and as you're getting more experience, be like, oh, I want to change this year, and change that portion of it. We have a teacher in my school who's probably in their 5th year, I think, at this point, and now they're starting to rewrite some of their units because they're like, I have new ideas on how I want to approach this, but they're not doing everything. They're doing a couple lessons here or there to kind of build that up. And sleep is really important because then you can function and get things done more effectively.
I love that. We're a big proponent of self-health. So yes. And on that, I know that a lot of people are isolated and don't have a lot of people to talk to. So I invite you, if you haven't joined our network yet, to please do so. I think we're over 800 people, so I am sure that you will find somebody to talk to. And I would like to thank you for taking the time, Danielle, to talk to us today. I know you probably didn't get to look at the chat, but a lot of people said they feel much more confident in what they're doing, and they're excited to go back to their classrooms and bring this stuff with them, which is always great. I do want to invite everybody. We are going to do a follow-up coffee talk for this talk on February 5th. It takes some time to process everything, right? And then about a week from now, all of a sudden you're like, I want to talk to everybody who was there because now I have this great idea. So we will be doing that. And then as Danielle said, on the 12th is the AAPT coffee talk, which I strongly encourage you, if you're thinking of giving a presentation. Danielle and I and Isa, we were all talking earlier, we're all experts. We all have something to share. And if more people share AAPT, we all get to take stuff home, which would be great. Boston is also a great place if you haven't gotten to go. And then we have our upcoming Climate Talk series, which will be posted in the chat, those 3 dates. Information on those will be coming out soon. But again, I just want to say thank you very much, Danielle, and thank you all for coming and sharing.
Thank you for having me.
Thank you so much, Danielle. That was just absolutely fabulous.
Thank you, Eric.
And you may want to look at the chat because it was. I literally had to split my brain in two, and look both at the chat and follow the links. It was so. Be sure that you save the chat.
I will
before leaving.
Yes, I absolutely will save it and then read it through.
Yeah. All right. I hope I'll have an opportunity to meet you in person, Danielle, and what you're doing has, a lot of overlap with what I'm trying to do. On one of your pictures, I thought I recognized a student who is now in my class.
Really?
Do you know of any West Windsor students who graduated and went to Harvard?
A lot.
Or are they all going to Princeton?
No, they go everywhere. They go everywhere. Do you remember which picture?
African American. She was. It was one of your first slides in that showed sort of student activities.
Oh, yeah.
She was on the far right, and
that's Frances Brown.
Frances Brown. That name doesn't ring a bell. So anyway, it would not be unheard of for that to happen for a student from your class to end up.
It would not be unheard of.
No.
It would not.
No. But anyway, if you're in Boston, please do before the end of my semester, which is the last week of April. Please do come and visit. I'm also so incredibly happy that you mentioned that you're using and that you mentioned team-based learning, because I am a complete convert to team-based learning, and I think we actually have a moral obligation to teach people how to work together. And it's probably a big failure of education in general at all levels, including in particular at the college level, to turn people into competitive individuals who compete with each other rather than collaborate with each other. And then we deliver them to society and things derail. And team-based learning, and this is actually one of Isa's research topics for her thesis, actually teaching people how to collaborate and get along with each other is important. And I think they should start very early in the curriculum and then continue through college. So I did a very quick poll asking, how many people are using team-based learning? I think the last I looked at it, there were 6, and then you and me. So that's about 10% of the peak audience we had today. Let's see, where is it? I'm scrolling back through the chat to see if the number increased, but I doubt it because, let's see, where is that? And I think there's really room for it. It's just, okay, there were 8 in the end. So, but it's still around 10% of the audience. And so we have 90% of people, and probably this audience here is much more inclined to try new things than, all of the teachers on the planet. So I think we have a long way to go to promote things like team-based learning at the secondary level or even at the primary level. Although I think the early grades tend to be much more collaborative than later. Competitiveness sort of increases as you go through your education, and then it sort of gets to a peak when you do the admissions test for college and the admissions test for graduate school, where people hate even helping each other. What are your thoughts there?
I think it's getting better. I think a lot of students are becoming more comfortable working together in teams. I know at least where I am, they kind of come to expect it. They're not expecting to sit as much anymore. I think it was difficult for them also coming back from virtual instruction because so much of that was individual because they could just hide behind their monitors for it. And I think as educators, I think there are programs out there that are definitely switching to more team-based. I think we just need to be able to connect with each other, and we need to be able to have more programs share out what they're doing. So other teachers may be like, oh, maybe I'm going to try team-based for this small thing and see how it goes. And then you build. Because you take it, if you start it once, if you start it all at once, it's going to be overwhelming.
That was going to be my next question. How are your colleagues reacting? But I guess rather positively.
They're positive to it. I think I do some more team-based instruction than some other people in physics, but I also do not like standing in front of the classroom. It's not who I am. I'd rather be walking around and working with the students that way. So for me, it seems more natural because I enjoy learning in that way, and that's how I feel comfortable. So I want my students to be doing it.
So when I refer to your colleagues, I meant not only in physics. What about chemistry, biology, history, you name it?
Very, very supportive of it.
Very supportive. That's great.
I'll walk around, I'll visit people's classrooms, and a lot of them have students sitting in groups, even if they're working.
Fantastic.
Someone there, so very supportive.
Fantastic. I have to make the post office before it closes, so I'm going to say goodbye to everyone. Thank you so much for coming, and please